All right, so here we go. Happy Monday. Let's do this thing. So we were talking about clustering last day. Let's just get right into it. Right into it without a review. All right.
I am a little curious about assignment 4.
Oh, yeah.
Have you talked about it before?
No, I think beyond just saying that I posted it.
Oh, okay.
I'm not
But
sure.
I guess everything we need to know is on there, right? So it's
yeah. It's a little bit different because it's on probability, so it's not like you can't make a ton of graphs or anything. When's it due? Do you guys know?
Wednesday, I think.
Wednesday. I can bump that to Friday, the 20th. Should we bump that to Friday? Is that better?
Well, either way, I'm gonna have to do the assignment and also because we have a quiz, right?
Mm-hmm.
So, I need to do them both. I might as well get one done sooner and then the other done later.
How about this? We've got quiz number 2 on Friday, but it's open until Sunday night. So
okay.
kind of you'll have the weekend whenever it works for you to do it. Open until Sunday night. You know what? I'm not even going to commit to the review yet. I want to clear this up. But then you also have assignment. Kind of lost track of what I'd made you do. So I'm just calling it the chapter 4 assignment. I think it's assignment 3, but that gets confusing. So it's the one for chapter 4. And it is currently due Wednesday. Thank you. But if that feels like quizzes, they're tough. Most of it is the time restraint, right? Freak out. But notice that the quizzes are just from class, right? They're not from R Studio. They're just theory materials, right? And so just as a reminder, only theory, no R. Sad face, cool face, I don't know. Okay, so the chapter 4 assignment is due on Wednesday, but if that feels like it's creeping up, what I am kind of leaning towards doing is if you haven't started, then maybe it's time to have a look at it at least. And then I'll bump it to be due on Friday night instead. And then if you have questions about it, you can ask me on Wednesday when you've had a chance to look at it, or any other time. You can just get in touch with me anytime. But quiz 2 is for chapter 4 and 5. Okay, so how's about we strike this from the record and we say instead it can be due on Friday, the 22nd. Okay, so look it over. And then if you do have any questions, I'm sure you're not the only one. So then if you do have any questions, you can bring them up in class on Wednesday instead. Because now if you're feeling like, I haven't even looked at it, that's crazy. Well, how am I supposed to know what to ask? Well, so that's why we're kind of moving it a little bit. That's fine. Or if you're working on it, you can always just get in touch with me and we'll clear it up. Okay. thoughts about,
I looked at it briefly and I noticed that we're required to make a code book. Have you talked about code books?
code books? How about this? I have not talked about code books, but a code book, you can Google it. It's just a list of all the variables and what type of variable they are and some common measurements. So what I'm going to do is I'm going to post an example of a code book. And thank you. I knew there was something on there that I had forgotten. I will post an example of a code book. I'll even include the markdown code so that you can just copy paste it. Awesome. See, everyone was wondering, what's a code book? Oh, I think I'm supposed to know what that is. No, we haven't talked about it. Good. There we go. And I say that, but I actually better write it down this time, because I feel like I've had this moment before where I thought, oh yeah, I'll post that. I didn't. Good. All right. So, all right. Any other secret questions that you're sitting on that everyone else is sitting on as well? Okay. How about come up with any questions for Wednesday's class once you've had a chance to really look at it? All right. So, quick review. The only thing I really want to review today is the k-means clustering, which is what we finished talking about, because today we're going to introduce the hierarchical clustering, which is the other type of clustering that we could do. Okay, and so k-means clustering. What does it do? We predefine the number of clusters that we want, right? And so I want to use predefined. Is that even a word? Predefine, predetermine? We pick? I don't know. You get the idea. Pardon?
I approve of this word.
I'm Nathan, I approve this message. Oh, the assignments. I know. I have been plugging away, had some other stuff come up, but what I'm doing is I am marking yours, but then I realized, oh, you know what, before I see any of yours and I'm clouded by, what I've seen, I'm making like my version, and I'll post the RMD file and everything so that you'll have kind of another version to see, and then I'll also give you feedback on that. So I'm working on that. I know I'm behind. You don't need to tell me I'm behind. I'm behind, but I'm working on it. So, but once I'm finished, you'll have more than enough to go off of. One thing that I will say is I'll post the RMD file, and there are a lot of comments in the RMD file that won't show up in the knitted document. So you'll definitely want to look at the RMD text as well, right, to get the full gist of what I'm doing, right? And whatever I post, you're allowed to use, copy, alter, whatever. Okay, so and then I got carried away. So then I was like, okay, I'm going to do a really basic one, kind of bare minimum answers. And then I want to do like an extra one where it's like above and beyond kind of what you could be doing, just so you have an idea of kind of the range. I know I get carried away with this type of stuff. Sometimes it's not a good thing. Sometimes it is though. And I won't do it for every assignment. It's just so you have something to go off of. Okay, so we predefine the number of clusters that we want. The number of clusters that we want, right? And so we want K clusters. Okay. Then initially, everyone's just randomly assigned to a cluster, right? And so initially, every observation is assigned to a cluster. Yeah. That's when we pick some sort of, the distance calculation, and we also calculate the centroid. And then so each cluster has a centroid, and then we don't do any of it. The machine does it, right? We tell it to do it, but we need to know what's going on behind the scenes, what we're asking it to do. And so initially everyone's just kind of spread out between these K, let's say 3 clusters. And then we calculate the center of each of these clusters. Calculate the centroid of each cluster. And then everyone just kind of scurries to whichever centroid is closest to them, right? And so that's when you need to define, okay, how am I defining distance, right? The closest, it could be, typically we use the Euclidean distance, it could be the Manhattan distance, right? And so it depends on what you're talking about, but just in general, every observation goes to the cluster with the closest centroid. All observations rearrange to the cluster with the closest centroid. Yeah. And then we recalculate the centroid, and then we do that again. Recalculate the centroid, observations rearrange. And then that repeats until there's no change. Repeat this until there is no change. Okay. Good. So that's k-means clustering. So the other type of clustering, which we kind of talked about, is the hierarchical clustering, where everyone starts as their own cluster, right? So instead of assigning everyone to a set number of clusters, everyone starts as their own cluster. And then depending on which values you're close to or which observations you're close to, you go in and you form a cluster, right? And so then we're not actually dictating the number of clusters that we want. They're just going to form by themselves. Okay? Before we leave k-means clustering, we finished and we said, okay, well, if you're not sure of how many, so what your K should be, so how many clusters it would be ideal, right? You can always run a couple of different scenarios, right? You could run, so one cluster would be your baseline, right? That's basically no clustering at all, right? And then 2 clusters, 3 clusters, and you can look at the differences within the observations of each cluster, right? And so if you're not sure of what value to choose or to use, mostly because I don't like spelling choose. I always use the wrong one, but I think it'd be a double O this time. So if you're not sure of what value to use, you can always run multiple scenarios. You can always run multiple scenarios and compare the within cluster variation. And compare the within cluster variation or variability. Yeah. That's easier said than done. The within cluster variability, there are lots of different ways that you could measure variability, but there are some key ones that, and I think there's probably a default one, but I don't know. Sums of squares, I think they used here. Yeah, sums of squares, which is the difference between the observation and the centroid squared, I think. Pretty sure it's in here, but I don't remember. Anyways, we're moving on. It's there. But let's talk about hierarchical clustering and dissimilarity. You know what? Start it on its own page here. So hierarchical clustering, this one's full of words that I have a hard time saying. Hierarchical is hard to say, but also agglomerative is hard to say. Luckily, they're kind of synonyms. And so another thing that we could do instead of the k-means approach is an agglomerative hierarchical clustering approach that starts with each observation in its own cluster and then iteratively combines the two clusters that are the least dissimilar into a single cluster. Least dissimilar is the same as the most similar, right? So it depends on how you want to think about it, right? The least dissimilar would be the closest observations, or the most similar is, of course, the closest observations. So whichever way you prefer to think of that. In fact, it doesn't matter. Okay. And so you might go through multiple iterations, right? Where you start with all your observations, and then you might look at combining just the most obvious observations, right, to make a cluster. Now notice that these cluster sizes are not the same size, right? They're not the same necessarily, right? And so there's a dendogram, but I think we hold off on it just a little bit. But a dendogram is just a visualization of how these clusters are formed. Okay? And so maybe what I'll do, and gets confusing because I found a total oversight in the textbook. This is not the right header here. Completely wrong. It's not what it is. I don't really know what it is. It's like 4 different ways of measuring the distance and how close a cluster is from another cluster. But just to show you what I mean is here. This is what we call a dendogram. Yeah. And so what we have are all the different observations down here. They're not in order because they've been kind of put together with their most similar observations. So of course you would probably start with observation 1, observation 2, observation 3, observation 4. You'd probably have them in order. So in the first iteration, what happens is that 4, 5, 6, 11, 19, and 28, it's hard to see, but these are connected by a line here. Okay, so those have been rearranged and put in a group together because they're very similar by some measurement. Okay, and then so at each iteration, right, we go through and we combine observations. So this one observation is just off on its own still. And then after some distance away from this other group of 4, 5, 6, 11, 19, 28, it gets combined with that group, right? So how I think of it is if I have, and all the things that we tend to sort are very similar, right? But if I have, let's say, gummy bears, right? I sort them probably by color. That's the most obvious thing that I can sort by, right? And then, so that would be kind of the first iteration. And then I can consider things like size. There's really not that much to consider for gummy bears, but I think it gives us a good idea, right? We have kind of the first initial sweep where we kind of categorize things, and it's the most obvious clustering that we can figure out. And then we say, oh, I've got this one gummy bear that doesn't really match the color of any of these groups, but I need to put it in a group somewhere. And so I'm going to put it in this group because it's the least dissimilar, right? Not necessarily the most similar at that point, but the least dissimilar, right? Kind of the closest group that you could put it in. Gummy bears was a bad example, but it's kind of a fun one to think about. So I think you get the idea though, right? Hopefully, because I can't think of another example. What else are we sorting? Legos? Legos are actually pretty good because they have different colors, they have different sizes, but that's about it. Anyways, everything for me ends after 2 iterations. That's all I can think of. But of course, the data, numerical data, we can go further. Anyways, so what we want to talk about is how do we create these groups? What are some of the methods that we can use to create these groups? So, oh, I was surprised that it wasn't highlighted, but I realized I'm in the wrong set of, or in the right set of notes, but in a different set of notes. Let's see here. There's the one I wanted. So here, just as a note, this is the wrong caption. Just who's going to email the publisher? You or me? No, get all up in arms. There's tons of typos actually in this chapter, which is really surprising because there haven't been previously, and now all of a sudden it's riddled with all these weird typos. So I feel like they farmed this one out. Didn't check their work. But anyways, so how can we combine these clusters, right? How can we decide what's close? And of course, we need to decide what the distance is. How do we measure the distance? Okay, so given a way to measure the distance between observations, for example, Euclidean distance, the Manhattan distance, the matching distance, or the Jacquard distance. Remember, those are for binary data, right? And so now we're talking about any sort of data, right? It doesn't have to be numerical anymore. And so, wow. Let's see here. The matching distance and the Jacquard distance is for binary data. whereas the Euclidean distance and the Manhattan distance were more for numerical data, or they were for numerical data. So it depends on what type of data you have, but now we can create these clusters regardless of what type of data we have. We just need to be able to calculate the distance. As a default, I would probably use the Euclidean distance for numerical data. Okay, and so here the Euclidean distance, and I'm not really sure. I would probably use the Jacquard distance as a default because it removes those matching zeros, right, which aren't necessarily the same. So it's a little bit fancier, right? Oh yeah, so once you've decided how do I measure distance, then you start asking, you probably start asking yourself, distance between what, right? And so there are lots of different methods that have been developed for, okay, well, once you've decided how to measure the distance, now you need to think about, okay, so what's going to be more important? And so some of the different ways that we can measure distance between two clusters, first one would be the single linkage. Now the single linkage takes the two most similar observations in the clusters, okay, and calculates that distance, right? And so if these two are really close together, then you would merge that into one cluster, right? Whereas the complete linkage looks at the points that are the furthest away from each other in two clusters. What's that distance? If that distance isn't very far, then we can probably combine those clusters into one and not lose a ton of information. Right? You can do fancy things like the group average linkage, which is the distance between each of the points in cluster 1 to a point to each of the points in cluster 2, and then you take the average of those. You could take the median of those. There's tons of different options, right? Or you can calculate the centroids for each of them, right? The centroids, we use those for k-means clustering. Those are the central values of each of the clusters, right? And then you can calculate the distance between those. Okay. So to determine which clusters can be combined, we consider the distances, and there are lots of different distances. So we consider the distance, and I'll put in brackets here, different options for those distances. Options below, we consider the distance between two clusters. Oops, that's the wrong two clusters. So the single linkage is kind of pretty basic. In fact, I'm going to bring all this in so we can have it. Uh-oh. Now I done it. There's no room. Start here. The distance, so single linkage is the distance between the pair of observations that are the most similar. So I like to imagine those circles that you have, right? And if the circles also show you the distance, right? So for example, let's see if I can pull this off. Might not be able to. A, B, C, and D. Yeah. So just imagine these are 4 clusters that you've generated already. And let's just say that the shortest distance here is the distance between A and B, A and C, and A and D, right? So you've got these distances, right? Looks to me like, so if we use the single linkage, what would happen is we would have A and B merged together, right? Like that, to make one new cluster, which I can't name because the other ones are A, B, C, D. Cluster 1, right? Whereas if we have complete linkage, then we're looking at the points that are the furthest away from each other in each of the clusters. So now, how can I draw this? Okay. Let's see here. I'm going to start with A here. And then I'm going to have B. B is this huge egg. Okay. And then C is here. And let's put D over here. I don't know. I just feel like I should always have a D. Who knows? So here, right, if we're talking about the complete linkage, well, then we're talking about 2 clusters as the distance between the pair of observations that are the most different. So in this case, if we want to kind of think about it visually, which is hard to do, right? Especially if you're me and you can't draw. But so in that case, we want to take the furthest observation from A and map it to the furthest observation from B. So here, that would be the distance between A and B. That's really far, right? Whereas if we consider A to C, right, the furthest observation from C to the furthest observation in C, notice that this distance is quite a bit less than the distance between A and B. And then of course, D is not getting lumped into anything with A, right? Might get lumped in with B because it seems to be pretty close to B. But if we kind of maximize the distance here, right, then I would combine A and C instead, right? So depending on how we consider those distances, right, complete linkage or single linkage, that's going to determine which cluster we're going to combine with. I could have, and I should have, used the same graphic up here, but it was an afterthought. So imagine you could have the same situation with A and B over here, because A and B, the closest observations here are still the closest, right? And you would still link with B if you were looking at the single linkage, but I'm just winging it here, so gotta cut me some slack. So that's the complete linkage. And then the other 2, the group average linkage and the centroid linkage, they're pretty similar, right? Oh, come on. So now it's hard to think about an average when we have multiple observations. But here, so the group average linkage, it takes the distances between each observation, right? And so observation 1 in A gets mapped, and you find the distance between all the observations in B, for example, and then you take the average of all those distances, right? So it's kind of where it's really hard for me to draw, but they did draw it here, right? And so the distance from observation 2 to 4, 5, and 6 individually, those would be in here, distance from 2 to 4, 2 to 5, 2 to 6, 3 to 4, 3 to 5, 3 to 6, 3 to 4, 3 to 5, 3 to 6, 1 to 4, 1 to 5, 1 to 6, and then you take the average of those, right? Or because you just have these numerical observations, these distances, you can find the median of those if you wanted to. So it's not restricted to just the average, right? So the median linkage is also an option where you talk about the median. Now, what's nice about the median is that the median, remember, doesn't care about outliers because it just takes the middle, the central value, right? And so it doesn't matter how extreme those outside values are, the minimum or the maximum, because those would be your outliers, right? And so the median doesn't care about those. So if you have kind of extreme observations, then you should use the median linkage method, right? If you want to avoid those. Okay. So, if you have extreme values, use the median linkage. And that's because it's resistant to outliers. The centroid linkage involves finding the centroid, which is kind of this weird thing, but really what you're doing is you're just calculating the average for each variable, and you're constructing kind of like an array or a vector. And if that doesn't sound familiar, you're just constructing a list with all the different averages, and then that's going to be your centroid, right? And then you can calculate the distance to another centroid. And so here the centroid trying to find where it says where does it say how we join them up? Obviously the closest, but I want it to say it explicitly. So here I'm going to add, because I'm just kind of scanning it here, but I'm not seeing it. So I'm just going to add it just to be safe. Join clusters with the closest centroids. Good. Of course, there's a lot of work going into finding clusters, and a lot of research is being done. And so everyone's coming up with their own way of clustering, which is fine. And so I just wanted to highlight that, not because I think, these methods are, I don't know, special in any way, right? But there are many other methods of clustering. There are many other methods of clustering. Right, so just as an example, there's Ward's method. where you partition so that you don't lose any information, or you minimize the information loss, which would be a concern, right? So what if you have this unique observation, and like we were saying with that gummy bear, what if I have one gummy bear that's a different color than all the rest, and I just end up putting it in some group? I decide, based off of some metric, right, size, color, whatever, which group it would be most similar to, right? But what if that one gummy bear that I am trying to figure out where I should put, what if that's a really important gummy bear that I need? And maybe it gives me a lot of information, right? Maybe it's this unique situation that I should be looking further into. Then when I lump it in with another group, I lose that, right? And so some Ward person, Ward's method, has figured out how to partition, so cluster, where we minimize the information loss. Okay. McQuitty's method, I don't even know what it is. I just wanted to show you that there are other methods and lots of other methods, okay? And so we compute the dissimilarity introduced by merging the clusters of A and B, and then we compare it to cluster C, I guess, and then we take A on its own, B on its own, and A and B merged together and compare it to C. Just other methods. Just some examples of other methods. And maybe I should change this to just a period, because those aren't the only methods. Those are just two that I'll just put in here. Yeah. So there are lots and lots of other methods that you could research and be overwhelmed by, underwhelmed by maybe. Hey, that seems obvious. Yeah, that's usually how it goes. Okay. So I want to show you that dendogram. I brought it up earlier, but now I actually want to bring it in, and I don't want to have this highlight on there. Copy. And I'm going to show you how to make a dendogram, because of course we can make one. It's a nice visualization for how our clusters are created. Right, and so here, this is a dendogram. So later, when I ask you to make a dendogram, it should look something like this. And again, I'll show you how to do it. But hey, I've been reading dendogram, but it's a dendrogram. Oh well. This whole time when I was reading it, dendogram, dendrogram. Who knew? I've never used a dendrogram before, but here we go. It's just a visualization of the clusterings. And so notice that you have the distance, which is whatever measurement. So that could be the Euclidean distance, right? The Manhattan distance, right? So however you've decided to measure the distance, that's going to be on the y-axis. And then you've got each of your observations down here on the x-axis, right? And so what we said before, and I wish I could kind of highlight this better. No. Maybe in pink here. So in the first iteration, right, that group of observations, those distances, right, between each of the clusters. So you start with each observation is its own cluster, right? And then once we group, we do one grouping, then these observations were, they decided that those are the closest ones that could be based off of the single linkage, right? Which would be what? The observations, well, with only one observation in a cluster, single linkage and complete linkage would be the same, right? Because there's only one observation. It's not until you have multiple observations. And so probably what we're looking at is the average of these two, right? It doesn't matter. The single linkage, you can calculate it because you only have one observation in each group, but it's going to be the same as the complete linkage. Okay. I'll make a note of that. Note, with only one observation in each cluster, initially, single linkage and complete linkage distances will be the same. Right, it's not until you have multiple observations in there that you're going to have different distances for the single and the complete linkages. Okay, and so what happened? Okay, so then what happened, if we just focus on this first kind of step here, is that this is roughly a distance of 0.25, right? And so what does that mean? It means that, well, it was decided that once we looked at all the distances, then the distance between this cluster, this pink cluster, and let's say this green cluster, observation number 1, and maybe I'll put the circle around the numbers so I'm not bunging it up. Okay, but what it's showing is that these two clusters were merged because they were found to be a distance of 0.25 away from each other. And that turns out to be the closest distance. Okay, in fact, that's the closest distance that any of these were merged away from each other. Okay. So all of these mergings happened at 0.25, except the observation at 25. So observation 25 held out for a little bit longer, right? So it was more different from all the other groups, right? But then eventually it merged with this cluster, which had already been merged. It's already two clusters merged, right? So here you've got a cluster of observation 2 and 26, and here you've got a cluster of observation 8, 10, and 20. Those were merged to make one cluster. Okay. Then we did another iteration. Okay, now 25 can join in there, right? But it was too far away to be joined up with 8, 10, and 20 initially. And even once we joined up here, right? And so each level here is going to be essentially an iteration. And so let's see here. Let me read to you. It's all here. I just want to make sure I touched on everything here. I did. Okay. Keep it small, but I'll zoom in here. So the vertical distance, right, up and down between the points of agglomeration is the cost of merging the clusters, right? How far away are these things before they end up merging? right? And so if we go back to, for example, well, this one's nice and, oh, sorry, it's catching up. This one on the far right, that one's a nice extreme example, right? And so here, it looks like 12 and 24 and 29, I'll make those an orange cluster. Orangey glad, didn't say banana. So here, I like it when you have your camera on, because then I can see how cheesy my jokes are. I'll be looking for a facepalm one day. Yeah. So anyways, so this cluster is so unique, right, in its characteristics that it held out for a really, really, really long time before we gave in and said, oh, fine, just combine it with this cluster here, right? And so this distance, right, the longer it holds out before merging with another cluster, we call that, I've got the word here, I want to say the stability, but I don't think so, the durability. A cluster's durability can be measured by the difference between the distance value, blah, 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 blah. And so here, this far one, so 12, 24, 29, that's that orange cluster, okay, is very durable because it took this long to combine with any other cluster, right? Making it a very unique subset. Okay. Another observation, but it's just one observation, is 25 is considered to be pretty durable because it took a distance of 0.35-ish to join up with these other observations that were kind of sort of the closest to it, right? But not close enough. Close but no cigar. So good. So that's kind of the idea, the theory behind clustering, right? Lots of different things going on here. It feels weird because we haven't applied it, and we're still not going to today. We're going to talk about association rules and potentially even text mining. We'll see how far we get, but check it out. We talked about a word cloud, and I found us one. All right, so word clouds are pretty fun. And what I've been meaning to do is try to find, because I know we have the transcript here, and I feel like that should be saved somewhere, the transcript of a class. And then we can make a word cloud out of all the things I say in class, and I'm scared. So anyways, we'll see if I can pull that off. We need the data first, right? But first we need to know how to deal with that data, because text data is different. It's a different beast altogether. But before we do that, we need to talk about association rules. Okay, so definitely in marketing, right? You want to know who's buying, a certain car, and how can you pick those people out of a crowd, right? And so those would be kind of association rules. Even in stores, right? They've got their brightest minds working on where they should put products, where should things go, so that we can see them when we're the most vulnerable, right? In the checkout line, why do they have candy bars there? Because we're going to buy them. They're impulse buys, right? And so, right. And so that's all come about from association rules and just kind of data analysis really led up to that, and then let it drop. Data analysis. Okay, so association rules are things like, if you are, and this is going to be very, very vague. Of course, we want to be more specific than this. But if you are a woman in the 30 to 40 category, myself, I'll leave it. I'll leave the age category nice and wide. Right. So if you're a woman in the 30 to 40 age category, then are you buying ramen noodles? I am. I love that Ichiban. And so, but probably not likely, right? And so, so things like that. So of course, all the stores are coming up with these loyalty programs, and that's just so that they can track, you know, all the things that we're buying. And you can even reduce it to things like, if they're buying beef, then will they also buy chicken, right? Should we have those things close together? We do, because it's cheaper that way, because we have a cooling disc that, or like a fridge section there, right? But I think I'm just thinking to my favorite grocery store. I think like the chips and salsa is pretty close by, right? Who decided that? Why is that? And then, anyways, things like that. So association rules require us to define a couple of terms. And that's unfortunate, but if you've done any sort of computer science, this will sound kind of familiar, right? We're basically going to have an if-then statement. Okay, and so if we have a rule like if this, then that. So for example, if a customer buys bread and jelly, then do they also buy peanut butter? Right? My purchases are always kind of staggered and out of control. So no, I don't usually buy them all at the same time. That doesn't mean I'm not having them together. So we can only get so much information out of it, right? But for example, so if the customer is buying bread and jelly, so those are 2 items. You can have more than 2 items, okay? But that's going to be called the antecedent, okay? And then the thing that we're interested in, right? So what we're interested in is the peanut butter. Who's buying peanut butter? Okay, and so that's called the consequent. And for now, the item of interest is the consequent. Okay, and so we only really talk about one consequent, because otherwise it becomes really mucky, right? If you kind of try to reverse these, right? Who's buying bread and jelly? Well, that's going to depend on multiple things, right? So you always want to have just one consequent that you're interested in at a time. Of course, then you could go back and you can consider other consequences. So only association rules with a single consequent is going to be considered, because they're more actionable. So what we're going to look at is how frequently do people buy bread and jelly and also peanut butter, right? But the number of people and how often people buy bread and jelly together, that's going to happen at some frequency. Okay, same thing with the peanut butter. And so that frequency, we call it the support. Okay? And so the support of an item is the percentage of transaction in the data that include that item set. Okay, and so I'm going to bring in this table so we can see what that looks like. So you're hard at work and you're analyzing this, I don't know, PC optimum data. Of course, there's a whole crew somewhere, so they're sitting somewhere, probably at home somewhere, and they're analyzing all this data all the time. Right? So what we want to do is we've got these just 10 transactions, okay? And we can see all the items that these people bought, right? And so we created a list. This is not typically how we store this data though, right? Because this is really messy. It's hard to read, but with only 10 transactions, we can go through and we can count, right? We can find the support for bread and jelly. So for example, here, I see bread and I see jelly. So that's 1. I see bread and I see jelly. That's 2. I don't see it. I see bread and I see jelly. So you can see how this order is so messy. You don't want to read this, right? And so think about how you would want to store this data instead. And that can be mind-boggling too. In the next one, I see jelly, but I don't see any bread. Here I see jelly and I see bread. Fruit, soda, potato chips, milk, no. Okay, so I see 1, 2, 3, 4 out of the 10 transactions, right? Create the support for bread and jelly. So 4 out of 10, which is 0.4, is the support for the set bread jelly. Whoops. Okay, so good. So that's how we define the support. It's just the number of transactions or the number of observations where we see that combination of purchases. Then, if we think about the support for bread, jelly, and peanut butter, it's at maximum, it's 0.4, right? Because it has to contain bread, jelly, and peanut butter. So now what I'm going to go through, and I'm just going to focus on the ones that have bread and jelly because I already know which ones those are. So that makes it easier to find the support for all 3, right? And so now I'm going to have peanut butter, bread and jelly, good. Bread, jelly, peanut butter. Here I see steak, jelly, soda, potato chips, bread, and fruit. So no peanut butter in this one. Okay, that's okay. And then here, jelly, soda, potato chips, milk, bread, fruit, no peanut butter, right? And so 2 out of 10, which is 0.2, is the support for bread, jelly, peanut butter. Okay. Now imagine you've got all that PC optimum data. That's going to be insane, right? But they have their own categories. And so typically this data would be sorted in some sort of present absence type of matrix. Okay. And so we would typically we would typically store this type of data in a presence absence. No. Matrix. And there are still a couple of different ways that you could organize the data, and it depends on what you want to do with it. But for example, what we could do is we could have the transaction number 1, 2, 3, down to 10. Okay, that's our observation still. And then for each of our columns, we can have, we can have bread. Bread was in transaction number 1. It was in transaction number 2. It was not in transaction number 3. And it was not in transaction number 10. Now I have binary data. We know how to find distances within binary data, right? We can find the matching distances, the Jacquard distance, right? So we know how to deal with this stuff, okay? But also it makes it a lot easier to find the support, right? Because I can just sum up the number of ones here for bread, right? I'd also need to have a 1 in the jelly column. So here I would have a 1 for the jelly, a 1 for the jelly. Observation, transaction number 3. No, they got whipped cream, fruit, chocolate sauce, and beer. That's a pretty fun transaction. But no bread and jelly. So 0. And then skipping forward to 10, 0. So you could create a column for each item, right? It might be tempting to lump all these items into just huge categories so you don't have to deal with it anymore. But then, of course, you realize, oh no, I lost all that information. So you want to have kind of a decent number of categories, right? And so, and we don't need to worry about kind of storage limitations anymore, right? Sort of, but not really. And so you can just keep a record of everything that people buy to analyze it. So milk 1. Transaction 3 has nothing in it. None of the things, right? And so here we can make this matrix, and then we can analyze this binary data. Yeah. Oops. Now, where did I go to? A rule of thumb. I really bungled it, didn't I? A rule of thumb is to consider, hey, I'll put it down here. A rule of thumb is to consider only association rules with a support of at least 20% of the total number of transactions. Yeah. And so you can kind of go beyond that if you want to, if there's something particularly valuable, right, that people don't buy all the time, or it's kind of an infrequent item, but you want people to buy that item because the markup is so great, and maybe you're interested in that item, then sure, you can change that rule. But a rule of thumb is to just consider at least 20% support. So I really like chanterelle mushrooms. So chanterelles, they have them in the store. I don't imagine a ton of people are buying them because they're dried and you want them fresh and whatever. But hey, you guys have them on the island. If you're on the island, no, you are. Then you should go find some chanterelles. Pretty fun. But anyways, so not a lot of people are buying them, but I can imagine that the markup is pretty huge. And so you would be interested in that. So then you might say, okay, yeah, it's okay that it has a low support, right? So a reliable association rule is that, okay, if I know that a transaction contains the antecedent, so the if portion, right, then there should be a high probability that it contains the consequent item set. Okay, so one of the problems that we need to think about is if I'm trying to say something like, if the person buys meat, then they're going to buy something really specific. Well, yeah, that's going to be pretty reliable in the sense that, yeah, of course, if you say, yeah, this person, did they buy meat? Yes or no? Yes, they did. Then, yeah, you're going to be buying these chanterelles maybe. But you want to be more specific, right? You don't want to have an item that's going to happen in every transaction, right? And so that's why you don't want to lump all those categories, all those food categories into too big of a group, right? Maybe you want to focus on, instead of saying meat, right, which would be everything from, well, there's all kinds of meat, but chicken, beef, pork, lamb, blah, 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 whatever. Right. And so maybe you want to focus on one type of meat, right? Maybe beef, and be more specific, right? Because, and then they've got an example of the fruit. So most people are going to buy some item from the fruit section, right? But that's not going to help you predict whether they're going to buy this fancy tea, for example, right? And so you don't want to have an antecedent that's too broad, okay? So a property of a reliable association rule is that given that a transaction contains the antecedent item set, right? So the butter and bread and jelly, for example, then there should be a high probability that it contains the consequent item set. So one way that we can calculate that and assign some numerical value to that is conditional, or the confidence, which is a conditional probability. So the probability of the consequent given the antecedent, well, if we think about our probability rules, kind of dust them off a little bit, that's the probability of the consequent and the antecedent, right? So in the peanut butter jelly time example, then we had the consequent and the antecedent. In that case would be the probability of bread, jelly, and peanut butter, right? And so in the example, this would be the probability of bread, jelly, and peanut butter divided by the probability of the antecedent, which is just the probability of the bread and jelly. The probabilities are going to be the support, right? We found those probabilities, if I say that 4 out of 10 transactions bought bread as well as jelly, then that's 4 out of 10, that's 0.4. That is the probability of the antecedent, right? And so you could rephrase it as the support of the consequent and the antecedent, which was 0.2, right, from before, divided by the support of the antecedent, which was 0.4. So the probability of the peanut butter example, given bread and jelly, oops, maybe write bread and jelly, is going to be 0.2 divided by 0.4. I'm just going to check here, which is 0.5. Grab this. I'll leave some of it for next day, but I'll just grab it all for now. Wow. So if we have a high value for the confidence, in this case, we have 0.5, right? Then it suggests that we have a rule where these things are associated, right? We're talking about association rules. And so it suggests that that's associated, right? But a high value of confidence can be misleading. So for example, if the support of the consequent is high, so this is what I was talking about, you don't want to have something too broad. So that is the item set corresponding to the then part is very frequent. Right, so you want to be trying to predict these kind of special cases, right? And so, oh yeah, the item set corresponding to the then part is very frequent, then the confidence of the association rule could be high, even though there's very little or no association between the items. So for example, if cheese then fruit has a confidence of 1 or 100%, but that's going to be misleading because almost any rule with fruit has a high confidence. Okay? And so I'll cut this off and leave it for next time. Okay, because I'm plumb out of time. If you have any questions, let me know. Otherwise, I'll see you Wednesday. No, I'll stop this. See ya.